Hello everyone. This video will be a short introduction into how to work with complex eigenvalues in the context of a system of differential equations. Okay, let's dive right into this. First off, we are given a 2 by 2 matrix, and this represents a system of two differential equations. Okay, so this would be something like dx dt equals 5x minus 9y, and this would be dy dt equals 2x minus y. The first step in the process is the standard procedure to calculate eigenvalues. So we begin by subtracting lambda from all of the values in our diagonal. And of course, the same is true whether it's a 2 by 2, a 3 by 3, whatever the size of the matrix is. It always begins with this step. Okay? And we then calculate the product of these two values and subtract it from the product of these two values. Okay? And as you can see, that was done here, yielding the following result. And moving on, I factored the result and ultimately calculated that our lambda minus 2 squared equals negative 9. And of course, as you should recall, this will give us a result where lambda equals the square root of negative 9. And of course, the square root of a negative number yields an imaginary number. So we wind up with this result for lambda, which yields these two results for our two eigenvalues. Okay, so eigenvalue 1 is 2 minus 3i. Eigenvalue 2 is 2 plus 3i. The next step in this process is to put together what is called an auxiliary matrix. And the process is fairly straightforward. It's just as easy as calculating a regular matrix. So we begin with our first eigenvalue, which is 2 minus 3i. And just like we subtracted lambda from our diagonal, we subtract that eigenvalue from our diagonal. Okay, and this row here simply means that we're setting it equal to 0. And this will be how we calculate our vectors. This is the result we get from this calculation. Okay, and now what we're doing is we want to, the ultimate goal here is to get our bottom row equal to 0. All right, but the first step in this process is generally to set this value here at the top left corner of the matrix equal to 1. So in doing so, we simply divide the first row by 3 plus 3i, which is of course the value here. That yields the following matrix. So we have our 1. We now have negative 9 over 3 plus 3i, and then 2 and negative 3 plus 3i. And now what we want to do is we want to take the complex conjugate of this value here in order to get this complex number out of our denominator. And we'll see how this will help us in just a moment. All right, so if you recall, an imaginary number is equal to the square root of negative 1. When you square an imaginary number, you get back negative 1. So here you can see the calculation, and it yields the following result. Okay, so we now have a matrix of 1, negative 3 plus 3i over 2, 2 and negative 3i plus 3i. Now it is a fairly easy process to get our two lower values to 0. Okay, so we're just going to multiply our top row by negative 2. And then we're going to add that top row to our bottom row, which will zero out the bottom row. Now keep in mind there were space constraints here, and I wanted to make sure that this was visible, so I wasn't able to fit the two zeros on the side here. but those 2 zeros should still be here in your auxiliary matrix. Okay. Okay, and now we have enough information to calculate values for K1 and K2. So as we see here, the calculation is fairly straightforward. All right. Our K1, which is represented by this first row here, this 1 in particular, since there's no information in our bottom row, so we can say that 1 times K1 plus this value, negative 3 plus 3i over 2 times K2 equals 0. Okay. Again, keeping in mind that we had our zeros here, and that is the purpose of it. Okay. And technically, we can actually consider the 0 to actually be a vector. Okay. And that will yield a K1, which is equal to this value, 3 minus 3i. We moved this negative value here to the other side of the equation. And so we get a value K1 equals 3 minus 3i over 2 times K2. And now we can simply select a value for K2. There's a lot of flexibility in selecting our value for K2, but of course we want it to have utility. So in this case, we can see that if we select a K2 equal to 3 plus 3i, we will actually get rid of this of the imaginary number in this case, and so we will have one real solution. Okay, so our K1 will equal 9, and if you do the calculation, I mean, you simply would multiply your 3 plus 3i to 3 minus 3i. All right, and of course, it's in taking that value over 2 will yield the following result. And you will see, for the sake of brevity, I did not go through the process for the second vector, but you will see if you go through the same process for the second eigenvalue, which was our 2 plus 3i, it will yield the following result. We'll get our K1 equal to 9 and a K2 equal to 3 minus 3i, as opposed to the result we just calculated, which is 3 plus 3i. So you can see the relationship here. And this will yield a result, the following result, okay? Now, I'm not going to go through the process of finding real valued solutions, but just know that this is not the end of the process, okay? This just yields the complex value general solution. And in general, we want a real value solution wherever possible. That's it. If you have any questions, please post them in the comments below, and thank you for watching.